Hi everyone, welcome to STEM in Places Introduction to Chemistry and Cookies. And this is part one of day two. So let's get started. What are we going to be doing today? Well, we're going to be discovering how our world is held together, pretty important. Mixing things up a bit. Is there a pun in that? Maybe. Learning about things that can melt your face off. Quite interesting, personally, I think. Connecting all of this to cookies, of course, and also conserving the mass of the universe with an experiment. So if you would like to participate in conserving the universe's mass, there's an experiment that you can do at home. So that's exciting. And then we also have here, don't trust atoms, they make up everything. Yeah, I don't know. I find all these jokes funny. I'm sorry. Okay, so here I have a YouTube video, which again was not made by me. I found it on YouTube, which kind of shows the molecules that we discussed in the past few videos in a more visual way. So you can kind of really start to see chemical reactions as, not just formulas, but as actual molecules combining and rearranging themselves. So I'm just going to play it.
What is a chemical reaction? To start with, all matter, whether it be water, salt, rust, carbon dioxide, or oxygen, is made up of atoms held together in unique ways, and we call these chemicals. In a chemical reaction, these atoms are rearranged to form new and different chemicals. Let's look at an example. In this chemical reaction, we have magnesium atoms being rearranged with a molecule of carbon dioxide.
And then as you can see here, so this is let me just get rid of this. This is the chemical reaction right here. 2 magnesium plus carbon dioxide gives 2 magnesium oxygen plus carbon. So, well, first thing that we can tell is this is balanced already. They gave this to us. So we know, 2 magnesiums, 2 magnesiums, 2 oxygens because of the subscript, 2 oxygens, and then just 1 carbon on each side. And then, we can see that the molecules kind of match up with the numbers. Since we have a coefficient here as a 2 for magnesium and we don't have a subscript, that means that we have 2 single atoms of magnesium. There's 2 of them, but they're not like connected. It's not Mg2. It's not, like the magnesiums are kind of independent of each other, and we just happen to have 2 of them. On the other hand, carbon dioxide, we can see that this is a molecule that is bonded together. So these are covalent bonds. This is just carbon dioxide again. And we see that there's 1 carbon and 2 oxygens because the O has the subscript of 2. But this is different than the magnesium because, again, magnesium has a coefficient, so that just kind of gives you the number of individual molecules or atoms, versus carbon dioxide has no coefficient, so that means that it's 1, and so we have 1 molecule of carbon dioxide.
And those atoms now make a chemical called magnesium oxide plus carbon. Let's look at another example.
And so there you could kind of see how, we kept the number of atoms of each type the same, but the bonds in the carbon dioxide broke and new bonds formed between magnesium and oxygen. And this happened twice, resulting in 2 molecules.
In this chemical reaction, we have hydrogen gas and oxygen gas, and they're being rearranged to form molecules of water.
And then here again, you can kind of see how it's just chemical reactions is just bonds breaking and then new bonds being formed. All right, so now we're going to be talking a little bit about how to read chemical reactions. We know how to balance them. We know, okay, we need to have the same number of each type of atom on this side of the arrow and on that side of the arrow. But that doesn't really help us when we have to kind of use chemical equations, when we're like, okay, what does this mean? So we're going to be doing that today. So here is our arrow, right? And that just basically tells us we're going from this side to that side. but each side kind of has specific names. The left side of the arrow is what we start with, and that's called the reactants. So they're called the reactants because they're the things that react in the chemical reaction. And so here the reactants would be 6 carbon dioxides and 6 waters. And then the arrow, if you're reading it, you kind of just say yield. So that's kind of, these reactants yield these products. And then the products are the results, it's what is produced in a chemical reaction. So if I want to kind of read this chemical equation out loud, I would say that 6 carbon dioxide molecules and 6 water molecules react and yield 1 sugar and 6 oxygen gas molecules. And then we also have, so again, these are the reactants on this side, and these are the products. We also have our coefficients, which is the number of each type of molecule. Remember, they affect all of the atoms after them, kind of like, for example, the 6 affects the carbon, but also the O2. And that's kind of just the number of molecules of each type. And then these subscripts are, again, the number of atoms, and they just affect the element directly before them. And then we had seen all of this yesterday. And then we also have a new thing, which are kind of these letters in parentheses. Sometimes they're there, sometimes they're not. It just depends on what your chemical equation is. And these are the states of matter. So I'm pretty sure that everyone has heard of these first 3 states of matter. We have solid, liquid, and gas. So if you see S, L, or G in parentheses, that's what that means. So for example, 6CO2G means that these are 6 carbon dioxide gas molecules. 6H2OL means that there are 6 molecules of water and they're liquid. And then again, this is a sugar. And since we have an S in parentheses here, we know it's a solid. Sometimes you'll also see this kind of weird one, which is AQ. That means aqueous. So that basically means that something is dissolved in water. So for example, if we were to dissolve salt in water, we grab NaCl, which is table salt. We have this S here, which means that it's a solid. We put it in water, and then we get sodium ions, aqueous, because they're dissolved in water, and then also aqueous chloride ions, again, also dissolved in water. Sometimes, they're not, the states of matters aren't given, but they are important for some reactions because, for example, sometimes the product will be a gas, and so you can't really see that. If you were to combine carbon dioxide gas and liquid water, you would only be able to see the sugar as a product, but there is also the oxygen gas that you need to take into account for like math calculations and such. So that's why states of matter are important. And now we're going to be discussing the different types of chemical reactions. So there's 5 common types. First off, we have combination reactions in which you have an atom or a molecule, and then you have another atom or a molecule, and then you combine them. So for example, we have molecule A plus molecule B, and that gives us one product, which has both A and B. So, that gives us this AB molecule. Decomposition reaction is the opposite of this, which is when we have one molecule or one compound as a reactant, and then the product is it being broken up. So if we were to continue using A and B, the reactant would be AB. So let's say that sodium is A and chloride is B. So this is AB. And then it decomposes in a decomposition reaction to form A and B. So again, these two are opposites. Here, combination, you're grabbing 2 or more things and you're putting them together. Decomposition, you're grabbing one thing and splitting it up. Then these other 3 are kind of a little bit trickier. This one is called, type number 3 is called a combustion reaction, which is basically lighting something on fire. Very exciting, I know. Personally, lighting stuff on fire is fascinating for me. Never mind. Okay, so combustion reaction, what you basically do is you are lighting something on fire, but that's not always evidence just looking at the chemical equation. So what you're going to have in all combustion reactions is you're going to have something with C and H. So some type of compound with C and H. It can be, it doesn't just have to be CH. It could be, for example, C2H2 or C2H4 or something like that. So it's just CXHX with these X's being anything you want them to. Plus, you have oxygen gas always. And then here, I'll draw the 2 as a subscript so that it's clear. And then the results are always, the products are always going to be the same. In a combustion reaction, you are always going to get carbon dioxide and water as your products. And this is actually pretty interesting when you think about it, because when you light something on fire, you don't automatically, you don't think that you get water, because water and fire, we think of them as to be opposites. But this is, again, why states of matter are important, because this water that results from the combustion is actually gas. So when you light something on fire, you have some sort of flammable molecule, which is made up of carbons and hydrogens. You add oxygen gas to it, or, well, it reacts with oxygen gas in the air. And then you get gas, carbon dioxide, and gas, water vapor. So that is combustion reactions. The easiest way to identify it is if your products are carbon dioxide and water, it's going to be a combustion reaction. And then also oxygen is a reactant. Then we have a neutralization reaction, which is basically you have an acid and a base, and that gives you water and salt. So I know this is kind of confusing because we haven't gone over acids and bases yet. However, we will really, really soon. But basically, when you have something with an H plus something with an OH, because typically, it's not always the case, but typically when something has a hydrogen, it is an acid, and when something has an OH, which is called a hydroxide, it is a base. So acid and a base gives you water, which is just H2O, and salt. The salt is actually, in this case, it's table salt, but that's just because we use HCl and NaOH, although this salt can be, like, it doesn't have to be sodium chloride. It can be another type of salt. This is just table salt, but there's many different types of salt out there. And then the last type is a displacement reaction, which is when kind of things switch places. So if we were to have molecule AB plus molecule CD, right, and we were to have a chemical reaction out of that, we see that there's kind of like a molecule at the beginning. Oh, there you go. There's a molecule at the beginning, which in this case is A, and in this case is C, and then there's a molecule at the kind of end. So in this case it's B, and in this case it's C. Well, basically they're going to kind of switch around, right? So they're going to switch places with the one that corresponds to it, if that makes sense. So for example, we see that we have like each molecule here is made up of one red letter and one orange letter, red being A and orange being B, and then red being C and orange being D. And we are going to switch these. We're going to switch the reds or switch the oranges, and then the results will be CB plus AD. So basically what's happening here is this is usually for ionic bonds. And remember how we said that ionic bonds always had a metal and a non-metal? Well, what we're doing is we have to make sure that our products have both, all of the products have both a metal and a non-metal. So what we're doing is we're kind of switching the metals or switching the non-metals. So for example, here is an example of a displacement reaction. So we have AgNO3 plus sodium chloride, and then we see that the sodium is a metal, and then silver, which is Ag, is also a metal. So they're switching places to make sure that that you get two new products, but that each of the two new products has both a metal and a non-metal. This is like a real, like I'm oversimplifying things, but that's just kind of to make things easier. So if silver were A and NO3 were B, and then sodium were C and chloride were D, we see that instead of having AB or Ag with NO3, we now have AD, which is silver with chloride. And then same thing happens with, they just kind of switch places. So basically, again, displacement reactions is just the two kind of atoms at the beginning switching places, or the two atoms at the end switching places. You're going to get the same result either way. Okay, so I said that we were going to talk a little bit about acids and bases, and we are going to talk about it. So you may or may not have heard of something called the pH scale. So here it is, and the pH scale is basically a measure of how acidic or how basic something is. So right here, we have a pH of 7, and a pH of 7 is a neutral pH. So what that means is pH of 7 is kind of like you remember how we talked about how protons have positive charges and electrons have negative charges? Well, a pH of 7 is neutral, just like neutrons, just no charge. It's not an acid, it's not a base, it's just neutral. Now, anything below that is going to be an acid. So 7 is neutral, but basically 6 and below is going to be acidic. And 8 and above is going to be basic. Or, a base is what I mean to say. So, and basically the further you get from 7, the more acidic or the more basic something is. So if I have a pH of 13, for example, and a pH of 8, we know that the further from 7, the more basic something is when you're increasing. So here a pH of 13 would be more basic. That's basically how you say it. It's like more acidic and then more basic. It would be more basic than a pH of 8. And then opposite things happens when we talk about acids. The lower the pH is, the more acidic something is. So something with a pH of 1 would be more acidic than something with a pH of 6. So that basically kind of covers the pH scale. So again, we have acids that have a pH of less than 7, and then bases that have a pH of more than 7. Acids usually have one or more H's at the beginning. So for example, we have HCl and HBr. This is hydrochloric acid, and I believe this is called hydrobromic acid. Versus bases usually ends with an OH. So for example, here we have lithium OH, and by the way, OH is called hydroxide, LiOH, and NaOH. Acids usually taste sour, like lemon. For example, we have here lemon juice, which is pretty acidic. Also, orange and tomato, the citrus fruits are pretty acidic, while bases tend to taste bitter. So for example, soapy water is pretty basic, and then seawater is a little bit basic. So basically, bases are kind of like bitter. Basically, if something like tastes soapy, that's probably a base. And both acids and bases can basically burn your face off if they are acidic enough or basic enough. What this means to say is acids and bases, extremely acidic and extremely basic substances, can be very dangerous. So be careful around acids and bases. So like, for example, seawater with a pH of 8 might not be very basic, But if you have pure bleach or if you have pure gastric acid, that could be dangerous, so be careful when dealing with acids and bases. So we're going to briefly talk about neutralization reactions again, now that we more or less know what acids are and what bases are. So remember how we said that acids typically started in an H. So here we have hydrochloric acid, which we can see because it starts with an H, and then bases typically end in an OH. So here we have sodium, the base with sodium in it, and we can see that it's base because it has a hydroxide. So this is sodium hydroxide and hydrochloric acid. Now, this is basically, neutralization reactions are basically just displacement reactions. But since they involve acids and bases, we give them a special name. Because if we really kind of see, we have here a metal. Well, I mean, hydrogen isn't really a metal, but it's looking to lose electrons. And then we have sodium also looking to lose electrons. And on the other hand, we have chloride, which wants to gain electrons, and hydroxide, which is a little bit more complicated, but we're going to treat it as kind of wanting to gain electrons. And then here we can see that for the products, the H and the Na just switch places. As we can see here, they kind of just switch places, and that gives us NaCl and HOH. But HOH can just be rewritten as H2O because we see that the subscript means that there are two H's, and this is basically just water. So again, neutralization reactions are basically just displacement reactions, but we give it a special name because acids and bases are extremely important in chemistry. And these reactions in general are just extremely important in chemistry. So we're going to do a bit of practice. Feel free to pause the video and try this out. We're going to determine whether these reactions are combination, decomposition, combustion, neutralization, or displacement reactions. So feel free to pause and try it out. And I'm going to be going over it now. So here we have 2 magnesium and oxygen, like this is oxygen gas, combining, and they make 2 magnesium oxide. Well, I noticed that here we have 2 reactants and that they combine to make a single product. So this is actually going to be a combination reaction. I should have probably changed that. Yeah, there we go. So that's going to be a combination reaction. All right, awesome. Well, on to the next one. Here we have hydrochloric acid. So I noticed that it's an acid, so I'm just going to underline that H, plus sodium hydroxide. Okay, so there's an OH. So we have an acid and a base. And this is giving us table salts and HOH, which is H2O, which is water. Well, since we have an acid and a base and they're combining to give us salt and water, I know that that is the definition of a neutralization reaction, which is also a type of displacement. By the way, neutralization reactions are called neutralization because you have something with a low pH and something with a high pH, and then the results, like the products, is, since it's water and water has a neutral pH of 7, it's neutralization because the products have a neutral pH. All right, well, on to the next one. Here we have zinc and 2 HCl2s. Okay, and that gives us H2 plus zinc Cl2. Okay, well, something that I'm noticing is that zinc, it's not combination because we don't go from 2 to 1, we go from 2 to 2. And it's not decomposition either because we're not breaking anything apart and, like, you know, we're not just separating things. So I know that it either has to be combustion, neutralization, or displacement. We do have an acid here, we see that there's an H, but zinc is not a base, so it can't be neutralization. And also, since the products are not water and carbon dioxide, it can't be combustion, so this has to be displacement. But we can actually see that because zinc and the hydrogen are switching places. We go from zinc being alone and then hydrogen being with chloride to hydrogen being alone and then zinc being with chloride. So this would actually be a displacement reaction. Then for number 4, we have 2HgO. Hg is mercury. It's a metal. And then that gives us 2Hg plus O2. Well, I noticed that what happened was this was basically just broken up. We had one, and now we had one reactant, and now we have 2 products. So that's going to be a decomposition reaction. And because basically we're just grabbing this molecule and breaking it up, nothing else happens. Then for number 5, we have H2SO4. I noticed that this is an acid because it has an H. Plus 2NaOH. Okay, so this is a base because it has an OH, and we've actually seen this base before. It's just sodium hydroxide again. And that gives us Na2SO4, which is a salt, and water, which is a liquid. So once again, because we have acid plus base gives us water and salts, this is a neutralization, which is also a displacement. And lastly, we have over here, we have C3H8 plus 5 oxygens gives us carbon dioxide and water. And since I know that we are getting carbon dioxide and water and that we are using oxygen as a reactant with some molecule with carbon and hydrogen, we are lighting something on fire. So this is going to be a combustion reaction. Awesome. Well, now we're going to briefly kind of switch gears and talk about covalent bonds. So all of these chemical reactions are basically just bonds being rearranged. You're either creating new bonds like happens in reaction 1, or you're breaking bonds like happens in reaction 4, or you're doing a combination of both. So it's important to talk about bonds and what they do and what their properties are, because if we determine how bonds behave, then we can also determine how chemical reactions are going to happen. So in a covalent bond, electrons are shared, right? I mean, we discussed this last time, how we have, for example, this is hydrogen, and this is oxygen. Oxygen is missing 2 electrons, and each hydrogen is missing 1, so they decided to share this electron pair between these 2 atoms and this electron pair between these 2 atoms. But we've talked about it as if electrons were shared equally. So electrons are shared in covalent bonds. That is what's happening, we can see here, but they're not shared equally. So what does that mean? Well, it's like, for example, if I decided that I was going to share, say, I don't know, me and my friends are buying a bicycle together, and we decided that we're going to share the bicycle. So like, you know, she gets it some days and I get it some other days. But maybe that doesn't, just because we're sharing it doesn't necessarily mean that it's going to, that I'm going to get it in equal amount of time as she's going to get it. For example, I might get it for only 2 days and she might get it for 5 every week. So that basically happens with electrons too. This pair of electrons is being shared. Oh, wrong pen, sorry. This pair of electrons is being shared, and this pair of electrons is being shared, but maybe they want to spend more time with this molecule and only weekends with that one or something like that. Basically what I'm saying is, you know, they don't spend an equal amount of time exactly in the middle between this atom and this atom. They kind of spend more time with one or more time with the other sometimes. Electronegativity determines who gets the electrons more time, basically. So electronegativity is the measure of how much an atom can pull a shared electron to itself. The higher the electronegativity, the more that the electron is going to be pulled to that atom. So for example, well, actually over here, we can see a periodic table that has the electronegativities of every element. The more kind of reddish it is, the higher the electronegativity, and that means that it can pull a shared electron to itself more. And then the more kind of greenish it is, the less electronegativity, so it can pull a shared electron to itself less. So over here, I know it doesn't say it, but this is water. So this is going to be an oxygen atom, sorry. And this is going to be a hydrogen atom, and this is going to be another hydrogen atom. So if we were to find them on our handy little table, periodic table of electronegativity, we can see that hydrogen has an electronegativity of 2.20. So it's kind of yellowish, it's kind of in the middle. But oxygen has an electronegativity of 3.44. So it's like bright red. It has a really high electronegativity. Since oxygen's electronegativity is so much higher than hydrogen's, these shared electrons are going to spend a little bit more time with oxygen than they are with hydrogen. And that basically is going to make oxygen a little bit more negative and hydrogen a little bit more positive. Because oxygen, it's sharing, it has its own 6 electrons, and then it's sharing these two and it's sharing these two. But since it is sharing, but since it has these electrons for longer, it's going to have a kind of negative charge. So the way that we indicate it is we draw this kind of weird looking thing, which is a delta, and then we put a negative sign to say that it's not fully negative, it's just kind of negative, because these electrons prefer to spend more time with oxygen. And then for hydrogen, the opposite happens. It used to have 1 electron, and now it's sharing 2. But since the 2 electrons spend more time with oxygen and less time with hydrogen, we see that hydrogen is kind of positive. So the delta here, this weird symbol that I'm attempting to draw here, I'll try to draw it a little bit bigger so you can kind of see it better. It looks kind of like this. That's still a pretty bad drawing, but basically that means that it means partial. So what we're saying is oxygen has a partial negative charge and hydrogen has a partial positive charge, which also applies to this hydrogen here. So we end up with a molecule that's kind of negative on this end and kind of positive on this end and this end. Almost like an ionic bond, not an ionic bond, kind of similar to it. So yeah, I just wanted to touch on that in this video, and next time we are going to be talking more about it. So hopefully you enjoyed, and stay tuned for day 2, part 2.